In this video, I'm going to explain the real reason why stick multiplication works, also known as Japanese, Chinese, or even line multiplication. While many might argue that this method came from China, Japan, or even India, I'm going to argue that it may very well have even originated right here in Ontario, Canada, considering how the curriculum suggests we might go about teaching multiplication. But just for the record, I really do have no idea where it came from, and nor do I really care. I do, however, really care about why this method works. If you think it's a trick, that's only because you're looking at it from a procedural perspective alone. It all starts back at the good old reliable method of organizing equal groups in rows and columns. You're right, I'm talking about an array. 3 times 2 is the same as saying 3 groups of 2, and we can show these 3 groups as 3 rows and 2 columns, or as 3 columns and 2 rows. Pretty cool, right? Here's another example. Here in Ontario, the grade 3 math curriculum tells teachers that we need to give kids a ton of practice working with multiplication concretely, and one of those very important representations is using arrays. As numbers get bigger, like 6 groups of 7, it can often be helpful for students to show the number of groups and number of items in each group, also known as factors like you see here. Note that the arrangement might look familiar, as this is often how we traditionally organize our multiplication tables or our multiplication charts. As we build this array, it's clear that one group of a quantity is equal to that quantity. Here, one group of 7 is equal to 7. Pretty cool, eh? And I can continue building these arrays to practice skip counting, visualizing doubles, triples, and all kinds of other useful skills that many back to basics advocates would love to see improved in our students. Now, while arrays are super cool, we're not here just to discuss the benefits of using arrays when learning multiplication. They can also help us understand why that stick or line multiplication actually works. We'll get closer to the reason when we start looking at larger factors, like 13 groups of 14. It would really suck if we had to build an array with individual tiles in this case. Luckily, somebody out there thought of base 10 blocks to make building arrays with large factors easier. Let's have a look at 13 groups of 14 again. Here, we represent 13 as 10 rods plus 3 unit tiles. So I've got one 10 rod and 3 tiles to give me 13. This reduces the number of manipulatives from 13 individual tiles to represent 13 to only 4 pieces. Pretty cool, eh? So as you probably guess, it'll take us only 5 pieces in order to represent the number 14, a 10 rod plus 4 single units. Now we can multiply in parts, focusing first on our 10 rods. Just like you do with a multiplication table, we can multiply 10 times 10 and see that the space the product occupies is 100. And with base 10 blocks, we can use a hundreds flat instead of 100 individual units, or 10 10 rods. Then we can look at the empty space in the top right of our array and note that now we have to multiply 10 from the factor of 13 by the remaining 4 units from the factor of 14 in order to get 4 10 rods, or a sum of 40. Repeating the same logic for the 3 remaining units from the factor of 13, we then multiply 3 by the 10 rod to get 30, or 3 10 rods, and multiply 3 by 4 to get 12 individual units, for a final product of 182. So let's do one more and then make a connection to stick or line multiplication. This time, we'll look at 12 times 15. So 10 times 10 gives us 100, or 100 flat. 10 times 5 is going to give us 5 10 rods, or 50. And we've now got 2 times 10 for 2 10 rods, or 20. And 2 times 5 for 10. And if we add up all of those partial products, we end up with a total product of 180. Pretty easy stuff, right? Now, let's go ahead and make the connection. First, I'm going to hide the values of the base 10 blocks since you've had some practice. It'll just clean up the screen a little bit. And now I'm going to really start explicitly outlining the gap between each base 10 block. So let's just spread them out a little bit. We're even going to toss in the lines now. And you might be seeing where this is going, because that line or stick method ultimately is right in front of our face right now. But let's get real explicit. I'm just going to separate our factors from the array just so we don't get confused. So you'll see that our factors are on the far left and at the top of the screen, and our product is in the bottom right, or the 100 rod and down and over. Now, basically, stick or line multiplication is simply skipping the step of drawing out the base 10 blocks by having you focus on the intersection of the base 10 blocks, or the sticks or lines. Prior to me drawing in all of these sticks, basically we were looking at the intersections of all the white space between the base 10 blocks. So let's shrink these blocks down and have a closer look. I'm going to shrink these guys down and really focus in on that intersection point. So my 10 times 10 gives me 100 up in that left corner. Now, if we look at 5 units from the factor of 15 and the 10 rod from the factor of 12, which yielded us 5 base 10 rods, or 50, we're going to shrink these down and we're going to show them explicitly that there are 5 points of intersection between each line representing those 10 rods. Do the same for the 2 units from the factor of 12 and the 10 rod from the factor of 15, and we get 2 10 rods, or 20. Again, producing 2 points of intersection. And finally, the remaining 5 units and the 2 units will yield 10 points of intersection, just like before we had 10 tiles representing that product. We're just going to put them right on top of the points, and now you can sort of see both the base 10 blocks and the lines or sticks representing our product. So there you have it. 12 times 15 is 180. Now, if you've never built a conceptual understanding of how multiplication works with arrays and base 10 blocks, the use of the stick method will always be a trick that will likely cause you errors and frustration at some point down the road. However, if you have a conceptual understanding behind why base 10 blocks work, you'll likely be able to use the stick method as a quick visual representation, which can serve as a conduit between the concrete and the symbolic standard algorithm. Now, why do you typically see the sticks from the line method tilted diagonally? Well, that's likely because many who are using the line method likely have no idea why it actually works, which is why you might need some assistance to organize the solution. However, it also suggests you're probably going to make some errors down the road, or possibly even forget why the procedure even works in the first place. So let's check this thing out. If I actually tilt this thing a little bit, what you're going to see is that your lines and sticks are now organized for someone who doesn't understand, because all you have to see is the intersection points organized by place value. Here's what I mean. The intersection point representing the 100 flat is to the far left when we tilt our sticks in such a manner. These points all represent the 10 rods in the middle, and these points in the far right represent individual units. So if we take a look at the sum, I have 100 in the first column, or the far left column. I have 70 in the middle column, and I have 10 in the right column. But if we're dealing with place value, right, that represents we have 100, we have 7 tens, and we have 10 units. Since we can't have a number greater than 9 in any column in base 10, we must trade in the 10 units for a base 10 rod, leaving us with 8 10 rods and 0 units. Now, while this is a pretty cool trick, it's also much more powerful if students could articulate where it comes from and why it works. Better yet, after students have a thorough understanding of arrays with base 10 blocks, I'd much rather challenge them to see if they could come up with an easier way to visually represent their 2-digit multiplication on paper without having to draw a bunch of rectangles and squares. Some might use sticks for base 10 blocks, and maybe, just maybe, someone in your class might come up with something similar to this stick method. How cool would that be? Oh, and before you go, you should know that using base 10 blocks to multiply is a great way to explain why the standard algorithm for multiplication works. Let's have a look. If we have a look at the array and the standard algorithm side by side, we can clearly see each step of the algorithm. First, we start with multiplying 5 by 2 to get 10. Then, we look at 5 times 1, but wait, it's really 5 times a 10 since that 1 in the tens column is to represent the 10 rod. So we get a partial product of 50. Then we move on to multiply 1 by 2, but wait again, the 1 represents a single 10 rod to be multiplied by 2 ones. That result will give us 20. And finally, the last partial product or chunk is multiplying one 10 rod by another 10 rod or 10 groups of 10 for 100 flat. Then we sum up the partial products and we arrive at our product of 180. While we're at it, we should probably make a quick connection to the standard algorithm we typically use here in Ontario, which basically has students chunking the first two partial products together, the 5 times 2 and the 5 times 10 for 10 and 50 to get a result of 60. Notice that we had to carry a 1 for multiplying 5 times 2, resulting in a 10 or a 10 rod. A similar 2 steps in 1 process is used when we multiply the 10 rod from the 15 with the 2 from the 12, giving us 20, and then the 10 rod from the 15 with the 10 rod from the 12 to give us 100, or combining those two to give us 120, all in that 2-step process. However, we still get the same result of 180. So while it might look a whole lot different than the array created with base 10 blocks, it really is a symbolic simplification of the process. Regardless of which method you feel is most effective and efficient for you personally, it's a great benefit to have a conceptual understanding as to why the method you choose actually works. In summary, I'd like to talk about concreteness fading, which is a theory suggesting that mathematical concepts are best learned in 3 stages. The inactive stage, where students use concrete manipulatives to represent the mathematical concept they're working on. Over time, after students have had enough experience physically working with the concrete manipulatives, they typically move on to the iconic stage, where they begin to often naturally draw visual representations of the concrete manipulative instead of having to physically hold and manipulate the object in their hands. As students become increasingly comfortable with the iconic or visual representations, it makes sense for them to begin using symbols that represent the meaning behind the previous visual and concrete representations. This stage is often thought to be the most abstract of the 3 stages because now numbers and symbols are used as an efficient way to represent the work that has been completed in the previous 2 stages. So what does the multiplication we just explored today look like relative to the 3 stages of concreteness fading? Well, when it comes to single digit by single digit multiplication using individual unit tiles, as we did at the beginning of this video, and physically arranging them into an array, over time, students don't have to grab those manipulatives anymore and instead start drawing what might look to be what those physical manipulatives look like on paper or in the mind's eye. And then finally, using more symbolic notation to do the work in their head. As we move to 2-digit by 1-digit or 2-digit by 2-digit multiplication, it would be useful to use physical base 10 blocks to experience what it looks like and feels like to multiply, possibly moving towards free virtual manipulatives like number pieces on the iPad by the Math Learning Center, the Ontario Ministry of Education's Mathies Tiles app, or the interactive manipulatives offered through the free Knowledge Hook game show tools. Over time, students will again begin to skip using the concrete manipulatives and opt to start drawing the array using base 10 configuration on paper and possibly in their mind. As they become proficient doing this, they'll begin using more symbolic notation such as this conceptual multiplication algorithm, known to many as partial products, but ensuring that students do not forget how to connect these pieces of the symbolic notation to the inactive and iconic stages of concreteness fading. Or students might opt to use the distributive property to chunk their factors into chunks that are comfortable for them, and start moving towards an open area model to show their factors and skip some of the inefficiencies of drawing each base 10 rod and unit tile prior to moving towards the symbolic representation of a standard algorithm. Again, noting that the area model and the standard algorithm is in fact the same process, but simply a different representation. And then finally, another possibility might be moving from physical base 10 blocks to drawing a visual representation like the stick or line method we explored today. And then finally, moving to some sort of symbolic representation. In this case, decomposing numbers using mental math and using the distributive property to multiply 10 by 15 and then the remaining 2 by 15. So I hope you found this video helpful to not only help you understand how the stick multiplication method works, but also to share the importance of building a strong conceptual understanding of mathematics through concreteness fading. As we're exposed to more ways to represent concepts in mathematics, our understanding of those concepts will continually deepen and produce more and more connections over time. There are a ton of other interesting ways to multiply. Please share some of those in the comments for others to enjoy. Thank you.